So today we're going to return to geometry, but more specifically circle geometry. And as you'll notice with the notes there, this is purely an extension topic. So you won't get any circle geometry questions in a 2-unit paper. So let's look at some definitions before we begin. Some specific ones for circle geometry. That's a circle. That's probably the key definition of them all. Right, so circle. A radius, now I know this sounds crazy defining radius, but we'll go through every piece. A radius is an interval which joins the centre of the circle to the circumference. A diameter is an interval that passes through the centre but joins 2 points on the circumference. So in fact 2 radii make up 1 diameter. A chord is just any interval that joins 2 points on the circumference. So a diameter is indeed a chord, but it's a special one that passes through the centre. But it is still a chord. A secant is a line that cuts the circle rather than just being an interval. So it still goes through 2 points of the circumference, but it extends through the circle. So that's the only difference between a secant and a chord. A chord stops at the circumference. A secant keeps going. Tangent, well, we certainly know what that one is by now. That line just touches the circle, so it only has 1 point of contact with the circle. An arc is just a piece of the circumference. Mind you, I've drawn in 1 arc there, but I've actually created 2 arcs. There's the minor arc, but then the bit that I didn't draw in, the bit that's left over, is the major arc. Now, when they're talking about arcs, we always assume they're talking about the minor arc, unless they specify otherwise. Right? So whether that be from their diagram, or whether they actually say major arc, and then we'll know. Okay. Sector, a piece of pie, some people think of it as, but it's a shape. Its boundaries are 2 radii and an arc. Again, I've actually drawn in 2 sectors there. There's the minor sector that I've labelled sector, but then the other piece is a major sector. And again, we would assume the minor sector unless they specify otherwise. So the minor sector is the piece of pie. The major sector would be if you're greedy. Now, a quadrant is also a special type of sector, but that's the one where the angle at the centre is 90 degrees. So basically there would be 4 quadrants in 1 circle. Right. A segment, the boundaries this time is a chord and a piece of the circumference and an arc. Once again, you can have a minor segment and a major segment. Okay. A semicircle then is also a segment because its chord is the diameter. It's also a sector if you think about it, because it also has 2 radii as a boundary as well. So a semicircle is all sorts of different things we could think of it as. Okay? Coneyclic points. So they're just simply points on the same circle. So all these points I'm labelling there, A, B, C and D, they're all on the same circle, so they are concyclic. Then there's a shape called the cyclic quadrilateral. And that's just a quadrilateral whose vertices are concyclic. So all 4 points are on the circumference of the same circle. Okay, so here's 2 parts of my circumference, so the arc AB I'm talking about, and I've joined it up to a point. That's what's called subtending an angle. So alpha is the angle I have subtended. So what subtend means, you get 2 points and you join it up to a 3rd point and you create an angle. So that's what subtending an angle means. So the way I would describe this is I'd say, well, alpha is the angle subtended at the centre by the arc AB. So I've got 2 points, the arc AB, I joined it up to a 3rd point, the centre of the circle. You may remember a circle geometry theorem that also subtends an angle at the circumference. And so beta there would be the angle subtended, but again, the same arc, AB, but at the circumference. Concentric circles, circles with the same centre. These two circles touch internally. So they will share a common tangent at that point of contact. So that's what we call an internal. They could just touch externally as well. They would also share a common tangent. It's also true, there's a theorem there that if you join up the two centres, they will always pass through that point of contact as well. All right, let's look at some initial theorems then. Chord, arc theorems. The reason I say chord or arc theorems is, if you think about it, when we talk about a chord or an arc, we have two endpoints. Well, equally, I could be talking about the arc or I could be talking about the chord because they both join up the points A and B. So often these theorems can be used as arc theorems or chord theorems. It doesn't really matter. So equal chords will always cut off equal arcs. So if you know the length of the chord is the same, then the arc that they cut off, the length of that must also be the same. All right, so the first one, a perpendicular drawn to a chord from the centre of a circle bisects the chord, and the perpendicular bisector of a chord passes through the centre. What on earth does that all mean? All right, let me draw a situation up. So here's our situation. If I know that line coming from the centre is perpendicular to AB, so that's the situation I've got there. I've got a chord, I've got a line coming from the centre, and I know they're perpendicular. Then I could say AX is equal to BX. And the reason I would say is, well, I know that the perpendicular from the centre will always bisect the chord. And so that's the theorem I would use. I'm going to go prove that. So all I know is that AB is perpendicular to OX. I'm going to prove that they are indeed equal. And you'll find most of these are done via congruent triangles. So I'm going to join up OA and OB to create a couple of triangles. And then I know, well, look, the angle AXO and BXO, they're both 90 degrees, so I've got an angle. AO is equal to BO, they're both radii, so they're equal radii. And OX is in both triangles. So I've got right angle hypotenuse side. So I know they are congruent. Well, if they're congruent, then AX must equal BX because they are the matching sides in those congruent triangles. So a fairly simple little proof there. So that's the first part. If we know that the line is coming perpendicular to the chord, then it's going to cut that chord off in half. Now, the reverse or the converse of that is this one. And let me draw that shape up. Say it was the other way around. What I knew was that AX is equal to BX. Then I could say, well, therefore, those two lines must be perpendicular. So it's like the reverse of the first one. The first one we said, if we know they're perpendicular, therefore these two things must be equal. Whereas this one's now saying, well, if I know these two things are equal, therefore they're perpendicular. So the reason I would use for this one is I'd say, well, look, I know the line joining the centre to the midpoint is always perpendicular to the chord. Let me prove that one. Once again, I'll do it via congruent triangles. So I'll join the AO and the BO up again, but this time I'm going to go, look, AX is equal to BX, that was given. AO and BO equal radii. OX is common, so I've got side, side, side. So yes, they are congruent. Therefore, AXO must equal BXO, but they sit on a straight line. So if they're equal and they sit on a straight line, well, I know they add together to give 180, so they must each be 90 degrees. So they are perpendicular. Equal chords are the same distance from the centre, and they subtend equal angles at the centre. Let's have a look at that one. So OX equals OY, and angle AOB. Let's have the picture there so we can see what we're talking about. Okay. So what I'm trying to prove is that OX is equal to OY. So the distance of the chord AB from the centre is equal to the distance of the chord CD from the centre. And remember, whenever we're talking about distances of a point to a line, we're talking about perpendicular distances. Okay? So the information that I know is that AB is equal to CD, and I know that OX is perpendicular to OY, not OY, I've written that down wrong, haven't I? OX is perpendicular to AB, and OY is perpendicular to CD. Because they're the distances we want to find. We're going to prove OX is equal to OY. You'll never guess how I'm going to do it. Using congruent triangles, amazingly enough. Okay, I'm going to join OA and OC this time to create a couple of triangles there. So AB equals CD. That information was given to me. The chords are of equal length. So AX would equal half of AB, because I know the perpendicular bisects the chord. CY is equal to half CD, perpendicular bisects the chord. I was possibly a bit lazy there. I should have really said perpendicular from centre bisects the chord. So therefore AX is equal to CY. Don't be lazy in your proofs. Okay? I know AB is equal to CD. That information was given to me. But I can't immediately say AX is equal to CY. I've got to prove that, because that information wasn't given to me. So that's what I've done there. I've said, well, I know that those perpendiculars bisect each of the chords, therefore the bisection must be equals. Okay, angle AXO is equal to CYO is equal to 90. That information is given to me. And AO and CO are both radii. Right angle hypotenuse side, I've now got the two triangles are congruent. So therefore OX is equal to OY. They are the matching sides in congruent triangles. Something to point out here about the setting out of our proofs, and I know some of us need some more work on that based on what we saw from geometry before. Think of your pages with a line that you don't have to draw a line down the middle, but there's a line down the middle. On the right-hand side is where you're putting your reasoning. On the left-hand side is where you're putting your working. It's not an essay where you just keep writing, oh, well, this happens because this and that. Oh, and then if I wanted to mark essays, I would have become an English teacher, okay? But I was smarter than that. No, see, I don't have to mark essays now. See, that was smart. That's what I meant by smarter than that. All right, I'm going to prove the other one now, that the equal chords will subtend an equal angle at the centre. This one's a bit easier to prove. Okay. AB equals CD, they're equal chords. That information was given to me. AO equals BO equals CO equals DO, they're all radii. Geometry is one of those exceptions. You know how it's been drilled into you over the years, oh, never have more than one equal sign on a line. And that's when you're working with equations. In geometry, it's okay, because we're just listing. We're saying, hey, all these things are equal. I don't have to put it in 4 lines and go, AO is equal to BO, and BO is equal to CO, and CO is equal to DO, therefore DO is equal to AO. It's okay to put it in one line and say, hey, all these things are equal, because they're equal radii. And therefore, I've got congruent triangles, side, side, side. So the angle AOB and COD become matching angles in congruent triangles. So equal chords. Now, here's another interesting thing about these theorems. We always assume we're talking about a single circle. But if you have 2 different circles of the same size, so they've got the same radius, then a chord of length x in one circle and a chord of length x in the other circle will still subtend the same angle in the different circles. So you could use this theorem in different circles. But you would say equal chords in equal circles. All right, so 9a, let's have a bit of a play with our chord and arc theorems.